What I'll tell you about today is focused on improving performance for magic needle spinning NMR, including probes and related hardware. And this is an odyssey that has gone on over my whole career, but especially over the last 5 years since I've moved to the NMRFAM in Madison. And this was a picture from June of 2019, which is when I looked into NMRFAM as a faculty candidate, potentially moving to the University of Wisconsin. And so obviously I have moved to Wisconsin, and we're transitioning where now half the facility is supporting solid state NMR. And unfortunately, my slide doesn't want to advance. So that is, okay. So we're applying a lot of solid state NMR methods to a wide range of biological systems. Is the reason that NMRFAM and other places have upgraded to solid state NMR capabilities. This includes microcrystalline proteins, amyloid fibrils, high molecular weight complexes, membrane proteins, RNAs, capsids, and many in the field. You know, you can name many of them, from Ann McDermott and Mark Baldus and Hartmut Ashkenaz, Mei Hong, Tatiana Polanova, Chris Juronic, and others have contributed substantial structures to this field, okay? And so when I moved to NMRFAM and was contemplating this move in 2019, John Markley was the director, Katie Hensler-Wildman was the co-director, and Sam Butcher is also a co-PI at NMRFAM. And at the time we had 9 magnets, as pictured here, and 4 of those in the main field, main hall, were unshielded. So 900, 800, 750, 600, as well as some other shielded magnets along the hallway. As part of my startup activities, we moved in a few Oxford magnets. We also moved a Varian 750 wide bore from Urbana as a first phase of installation. And then if we fast forward to 2024, when we completed the installation of 2 magnets down here at the end of the room, we have upgraded a 900 megahertz system that was moved from the University of Illinois Chicago, a 1.1 gigahertz instrument procured with NSF funding through the Mid-Scale Research Infrastructure Network for Advanced NMR. We have an 800 that is awaiting energization, and several other magnets that all was facilitated by major upgrades to the helium recovery system. And I'll tell you just a little bit more about this because it's really important in terms of the probe development to be able to have access to instruments at a range of fields. And so we've leveraged this capability at NMRFAM in order to develop better probe technology. And so here's a little bit more detail on the 900 system that was moved in August of 2022, and by March of 2023, it was brought to field. The 1.1 gigahertz came to field in November of 2023 and was fully commissioned. And sorry, that's a typo there. It's 2023, and then it was at field and accepted in December of 2023. You know, so now the final result of all these upgrades are that we have 4 new systems for solid state NMR. This magnet previously existed at the Vosges magnet. We installed Taurus and Ribeye and Ayrshire in this room, which are all Varian equipped spectrometers with Oxford and Magnex magnets. The 900 that I just showed you, which has a Bruker NeoConsole, the 1.1 gigahertz as recently installed, as well as a 750 megahertz magnet that came from the University of Illinois at Chicago. And so total, we've added about 50% overall increase in capacity in terms of magnetic field, and 6 of these instruments are dedicated to solid state NMR. Notably, part of this is also for the 1.1 gigahertz is a collaboration with Jeff Hoke at the University of Connecticut, Art Edison, the University of Georgia, and Katie Hensler-Wildman here in Wisconsin, and that paid for through the Mid-Scale Research Infrastructure Grant here for the Network for Advanced NMR. And now we have the solids dedicated instrument here in Madison. We have a solution dedicated instrument at the University of Georgia on the Complex Carbohydrate Research Center, and we have the NMR box and NMR hub capabilities at UConn, which hosts the Network for Advanced NMR, BMRB, and NMR box. Okay. I'll note also that some of you are aware that we received donations from the University of Illinois, which we greatly appreciate, both from the Urbana campus in July of 2020, the Chicago campus in December of 2021, and then again in July of 2022. And so we moved a 750 wide bore, an 800 US narrow bore, a 900 US tube narrow bore, and a 750 Ascend magnet. And those were compliments of Yoshitaka Ishii and others at the University of Illinois Chicago. And we had great service from the Bruker service team, especially Rich Griffiths, Doug Lyons, and John Snyder. And Reynolds was our go-to rigger. I went back and forth to Chicago a number of times during those years. And we were very happy to relocate those to NMR-FAM because otherwise they might have gone and been decommissioned because of the helium crisis. And because of the cost of helium operation, the University of Illinois Chicago decided it was better to transfer those to the University of Wisconsin. And so now they're available. The 800, we again hope will come to field this year, but these are all the others are available for the user program at NMR-FAM. And so we encourage you to contact us for NMR time, okay? And here's the floor plan that we ended up with. I won't say a whole lot more about that. There's some more pictures if you're interested. This is an example of the sort of resolution we achieve at 900 megahertz, which was upgraded to the Neo console. This is one of our staff scientists, Songlin Wang, who has collected, this is a spectrum of a large microcrystalline protein. And I'll say more about how we get to this in terms of resolution and sensitivity. But one of the ongoing challenges that I really want to focus on today is that of the performance at higher magnetic field, where the sensitivity does not scale as expected in many types of commercially available probes. And also the magnet stability and the resolution are challenges as we go to ultra high field. This is true both for solution NMR and solid state NMR. And so we want to address those points in turn. Okay. So just say one more thing about, I guess I have a couple more slides in here to show that the 1.1 gigahertz when it arrived in the summer of 2023 was craned into NMR-FAM. We had a lot of fun with the riggers, and in particular for this magnet, we had to first crane in a forklift, and then the forklift picked up the magnet and brought it over and put it on the concrete pad. There's Alex Patterson, one of our staff members, standing next to one of the legs. And so we were extremely pleased with Bruker's service through this installation and happy to get that to field and fully commissioned a little over a year ago. Okay, and that was November 17th, 2023 is when it came to full field. And then it was accepted in December and meeting all specifications for that system. Okay, and just one more picture about the helium recovery. Here is Paula Falco-Cobra, our staff member who organizes that effort. And in partnership with the University of Wisconsin facilities and Bruker, during 2023, we recovered a little bit over 20,000 liters of liquid helium. And so that was about over 90% of the total helium brought into NMR-FAM in that year. And of course, that was an especially busy year because we're energizing both the 900 and the 1.1 gigahertz. And as Frank Laukien likes to say, in a couple cases, we had multiple opportunities to bring magnets to field. And so this is also supported in a typical year at NMR-FAM, about 20,000 hours of user activity on the instruments. Okay, so there's the picture. Now, one more word about NAN. You can access not only NMR-FAM instruments, but also those at the Complex Carbohydrate Research Center and at the University of Connecticut and other institutions which are adding to the NAN network. And then you can go to the NAN site, usnan.nmrhub.org, and then you will find the ability to apply for NMR time. You'll be able to find resources at other institutions, including available magnet time. And we encourage you to apply, set up an account, and apply for time if you're interested. Okay. So now let's talk about probes. And the probe inventory for the 1.1 gigahertz instrument at NMR-FAM was selected as follows, with two Bruker probes for solution, a 3 millimeter room temperature probe, which was used to install the magnet, and a 3 millimeter TCI cryo probe for solution. We have that at NMR-FAM. We have the capability. Georgia has equivalent capabilities and keeps their instrument full-time in solution NMR. We also have a 0.7 millimeter HCN CP mass probe from Bruker, and we have a number of third-party probes. And I'll talk more about those because I know many of you are familiar with the available probes from Bruker, but I want to emphasize some of the custom capabilities that we've worked on over the last few years, both with Black Fox NMR and with Phoenix NMR. And so, as you may know, Black Fox NMR is a small company based in Tallahassee, Florida, led by Peter Gorkoff, based a lot on technologies developed at the Florida Magnet Lab. And Phoenix NMR is a spinoff of Agilent, where John Stringer and others who formerly worked for Agilent set up a separate company, Phoenix, to continue to support variant compatible probes. And so we have a Black Fox probe equipped with a 1 millimeter spinner. That spinner is provided by Phoenix and is compatible with the Varian 1.6 millimeter rotors. It contains a deuterium lock capability that I'll explain more later. The Phoenix 4-channel probe, HFXY, also has a deuterium lock. And a unique feature of the Phoenix probes is that you can swap out the head. And so here we have 3 different heads and actually a 4th one that is also compatible, a 1.6 millimeter, 1.2, 3.2 with the spinning and volume specifications indicated here. We also have a 5 millimeter head, although that doesn't tune for broadband tunability. It is available for some custom materials functions. Okay, so as I'll tell you more about for solid state NMR, I'll just briefly summarize an observation from Art Edison, and he gave a wonderful presentation last year at ENC showing progress with cryoprobes, and this is in collaboration with Bruker and again the Florida Magnet Lab. And what he's found in other sites with 1.1 and 1.2 gigahertz cryoprobes is that the sensitivity, although one would hope with 5 millimeter probes you could obtain sensitivity improvements at higher magnetic field, it turns out that due to the wavelength of that 5 millimeter coil set in a solution NMR probe, you gain much less than the expected increase in sensitivity as you go to higher magnetic field. If you go to a smaller solution NMR tube, you get closer to the expected improvement, omega to the 3/2 or the 7/4, and I'll say a bit more about which of those is applicable in each context. But so reducing the volume is one approach to getting some of the expected benefit of higher field, but that doesn't gain all of the benefit. And if in the solid state, for example, if we're using a 0.7 millimeter probe, we're potentially giving up a lot of sensitivity, especially for C13 detection. Okay, so my student, Eric Hahn, who's pictured here, he's currently now a postdoc, Eric Hahn in Sung-Hee Han's lab at Northwestern University. Eric did a PhD with me both at Illinois. Well, he started at Illinois and then moved to Madison and finished his PhD in chemistry here at UW-Madison. And Eric studied primarily this question of how can we get maximal sensitivity in a general way for solid state NMR that can be applicable to a wide range of use cases and user samples. And so as many of you of course know, the Zeeman energy is split between nuclear spin states, and this is proportional to the magnetic field. So one of the major contributors to sensitivity in NMR is that polarization difference in the high temperature limit. The Boltzmann polarization is essentially linear with the magnetic field. There are a lot of ways, as we know in the community, to enhance polarization through KidNip and dynamic nuclear polarization, and that is certainly a viable strategy in many cases. And so if you have compatibility with KidNip or DNP, certainly that's a great approach to handle some special cases, but there are many other cases that are not compatible with those polarization enhancement methods. And so we're interested in the general improvement and put from the perspective of a director at an NMR facility with many users coming to the facility, the majority of our users are asking for near room temperature data collection on samples that are not compatible with DNP or KidNip, okay? So now we want to understand how to break down this sensitivity, the equation from Holton Richards that was introduced about 50 years ago, and really understand how to control, how to measure, and then how to optimize each of these functions, okay? And so as noted, there's a contribution from the magnet, B0, and there's also a contribution from induction, and there's a contribution from the Q of the coil. There's a contribution from the spectrometer noise figure, from the probe, design of the probe, and the efficiency and filling factor of the resonator, and then there's a sample contribution. And so we'll take each one of these in turn as we talk about sensitivity improvements, because these are not all scaling with magnetic field as expected. In other words, when you go up in magnetic field and improve this factor, you might lose when it comes to this factor because you have to use a smaller coil. Or in some spectrometers, the noise figure may be compromised at higher field. And depending on how much sample you have available, you may want to work in a limit where you're sample limited and choose a rotor size appropriate for that application. If you have lots of sample, then of course you would go to the largest available rotor that's compatible with the types of experiments that you'd like to do, okay? So we would hope that theoretically we would achieve, experimentally, we would achieve this theoretical limit of signal noise improvement with B0 to the 7/4 when you add up all these factors. And in fact, we see that, and I'll come back and show how we get there, but this is the reason it's so important. Here, if we optimize the signal noise in 6 hours, this is an example of a 2D experiment on alpha-synuclein, and this shows a large number of long-range correlations, okay? If you were to cut that number in half, go down to half of that signal noise, you would only pick up a few of those peaks corresponding to the intra-residue correlation. So for detecting long-range distances in solid-state NMR structure determinations, as one example, it's critical to have this last factor of 2 in sensitivity. And as many of you experience on a daily basis, the time saving is proportional to SNR squared, or conversely, if you want to signal average your way out of low sensitivity, it's a very slow process. And so even to get an extra 10 or 20% is a really substantial improvement. And so we try to find every factor we can out of these equations, okay? And so Eric's published this study last year in JMR. And so this is a published result, but I do want to walk through a couple of the really key results to emphasize why we did this study and what the key findings are. And so one reason we did this study is because we were concerned that the reproducibility of signal noise measurements with standards that are often used in commercial installations are a little bit unreliable and show a lot of field dependence. So for example, glycine shows a strong decoupling dependence. Hexamethylbenzene has a very long T1 at high field. Adamantane is very sensitive to the shimming, which is an advantage if you're trying to shim, but a disadvantage if you're trying to determine signal noise. So all these things being considered, we've been using a standard N-acetylvaline, which is commercially available as a natural abundance compound. It can also be isotopically labeled for comparison to speed up data collection. The methyls are only moderately sensitive to optimization such as cross-polarization and decoupling and shimming. Although, of course, you always want to set CP and decoupling and shim the sample, you want to minimize that dependence when you're measuring signal noise. So the inherent T2s are very long for carbon. The T1s and proton are short. And therefore, you can use these 3 methyl groups, as we show in this paper, to get highly reproducible signal noise measurements that enable you then to probe the other contributions to signal noise that are not sample specific, okay? And the other piece of this that we had initially lots of problems with was getting reproducible noise measurements. So the irony of measuring signal noise is that it's usually quite straightforward to measure the signal intensity, and the signal intensity can be reproduced often to within a fraction of a percent. What is harder to reproduce is the noise, because inherently it's a stochastic variable. But then also, if you look closely at the baseline of any solid-state NMR spectrum under magic angle spinning, this is at 600 megahertz with NAV, with 100 kilohertz spectral width. That corresponds to about 600 ppm, which is a substantial spectral width. Nevertheless, you still see weak sidebands all the way across the spectrum and only have a few small regions that look like pure noise. Okay? Whereas if one were just to collect the noise spectrum separately, you'd have a much more reliable determination of that noise spectrum. And so what we do in practice is we collect a signal with cross-polarization, and we also can do this, of course, with a direct polarization signal. And then we collect a noise spectrum where we turn off the cross-polarization signal, run the whole phase cycle, end up with no NMR signal, but we apply the same decoupling and detect with the same spectral window and gain to get a proper noise reference. Okay, and so instead of using a 10% window, which also can increase the uncertainty, we would go to, and those are 10% windows, which are barely available in this spectrum, and also risk coming close to the edge where the digital filter may affect the result. If we want to use a larger region of 20%, we're going to run those sidebands. And so that's why we're using the separate noise spectrum, okay? And so Eric, along with Colin Borsick, a postdoc here in my group, worked out software to do this reproducibly. And what we find is that although when you measure the RMS noise with a 10% window, the signal intensity, the signal noise ratio has a larger variance on the order of 2.6%. It can be sometimes a little bit larger in value because if you use a smaller window, you can always, if you search around and find the minimum noise window, that won't be representative of the actual noise. If you use the pure noise, then you get a much more reliable number, and it's a variation of about 1 to 2% in typical use cases, okay? So now when we come back to this Holton-Richards equation, we ask ourselves, which of these parameters are under our control? Which of those have uncertainties that are substantial? And we want to tackle the shimming, the field drift, the amplifier performance, the magic angle, the spinning rate, cross-polarization decoupling. All these factors can contribute to the signal noise. So having a reproducible measurement is critical to be able to put together meaningful statistics where one can distinguish among these factors. So let me show you for example, what we mean by this. And we did a study, we being Eric primarily, and with the support of Peter Gorkoff at the National High Magnetic Field Lab and Black Fox NMR, and the group at Phoenix, as well as Kevin Gehring at Blue Sky NMR, who assisted us with some of the preamplifier reconfigurations. We went through a study of all the solid state spectrometers at NMRFAM, 3 600s, a 750, a 900, and a 1.1 gigahertz. And we evaluated a full range of probes, including 20-year-old probes that I moved from Illinois, new probes that we procured from Phoenix and Black Fox and Bruker. And we went through this with the same set of standard samples and the same protocols to get a high degree of reproducibility. Okay, so when you look at the raw numbers, at first it doesn't make a whole lot of sense, at least without making some corrections. Okay, so we know that if you, especially at low field, if you maximize the rotor size, 3.2 millimeter at 750 megahertz with the Ballon design, gives us the best overall sensitivity for NAV. The best at our 900 megahertz instrument is a Black Fox 2.5 millimeter, and that's in HC double resonance mode. And then we also have data at 1.1 gigahertz, but only at 1.6 millimeter. And the choices here, and this is typical of the situation that you would encounter if you want to apply, let's say 100 kilohertz decoupling as a benchmark, we can easily do that even with a slightly salty sample or with a thin wall rotor in 3.2 millimeter at 750 megahertz, but it becomes highly problematic to achieve that at 900 megahertz. And that's one of the reasons that the Bruker E3, although it's a 3.2 millimeter probe, has a greatly reduced sensitivity at 900 megahertz and 3.2 millimeter, okay? So in other words, we're maxing out, at least for now, with a 3.2 millimeter at 750 megahertz. That gives us our best overall sensitivity. If we go to 900 megahertz, we can get some benefit going from a 1.6 millimeter, which is here, to a 2.5. But then at 1.1 gigahertz, we decided with Peter, in considering the first round of designs, that we would go with 1.6 millimeter because that's what gave us the satisfactory decoupling of 100 kilohertz and gives us a sensitivity comparable to the 900 megahertz. So clearly there's some room for improvement there. And again, Eric looked at this, and when we first collected these data and started plotting them this way, it seemed like sort of hopeless to make sense of all this, okay? Although we could see some general trends, there were a lot of variations that didn't entirely make sense, okay? So what we went back to do is examine the Holton-Richards equation and do so with one parameter at a time. And so, for example, here, we're measuring the probe efficiency difference on a 600 megahertz, 1.6 millimeter sample of NAV. So we have 0.57 micromoles of carbon in HCN mode. And to good approximation, if you switch from HCN to HC mode, we can then determine that the difference in sensitivity is solely due to the difference in probe efficiency. So in other words, our pulse width, we measure in units of kilohertz per square root of watt. And so that would be 12.6 kilohertz per square root of watt in the case of HC mode, 9.1 in the case of HCN mode. So that's a difference propagating the error of about 40%. The signal noise difference, which is actually smaller than this difference, is about 38% plus or minus, okay? So the limitation, as we've learned, is actually measuring the power levels here, because the power measurements are not good to 3 significant digits unless you're very careful and use a NIST calibrated power meter. And so we're going back and reproducing some of those numbers, but this is the dominant uncertainty, is the measurement of the power, okay? So then the other factor, which becomes significant at high field, is the proportionality of the signal noise to noise factor, noise figure. And so this is on a 900 megahertz Avant 3 system. When we first installed the probes, we had a noise figure of 3.9 dB. We worked on, I'll show in a minute how we did this. We worked on that receiver noise figure and improved it to 2.3 dB by insertion of a third-party preamplifier in line with the Bruker preamp. And we gained that ratio of 1.6 dB noise figure, which if you plug into the equation, you would expect an improvement of 20%. And in fact, what we see is an improvement of 19 plus or minus 3%, okay? So again, the noise figure tracking follows. And that was, by the way, performed this way. So the noise figure depends in a cascade of preamplifiers, will depend upon the noise figure and the gain of that series of preamplifiers according to this equation. And what you have in this case is a preamplifier on the Bruker front end, which is F1G1, and that noise figure is about 2 dB, and the gain is about 30 dB. But if you just then run a cable from here over to the other side of the room, and please note, this is a 900 unshielded magnet that we were working with at the time. So that cable's about 10 meters. There's going to be a significant loss, and that contributes 1.6 dB to the noise figure. If instead one inserts a low noise third-party preamplifier, so this is an advanced receiver research gallium arsenide field effect transistor, it has a noise figure of 0.5 dB and about 30 dB of gain. You put that in line with the Bruker preamp, and now the losses of these cables are no longer contributing to the noise figure. You get a 1.6 dB reduction in the noise figure, and you also avoid the strong dependence of the noise figure on the RG value in the Bruker receiver, okay? So then let's go back and review the data once we correct for those. And so what we do is we're going to normalize here by the amount of sample, and we're going to correct the signal noise according to the noise figure and the probe efficiency, or to the noise figure. And what we see then is that the Black Fox 1.6 probe at 1.1 gigahertz gives us the best mass limited signal noise. We have, I should note, not yet completed the preamplifier upgrade on the 1.1 gigahertz. We believe the noise figure in our measurements is similar to what we saw in the 900 prior to upgrade. And so that's a disadvantage to the 1.1, but we still see some improvement. And if we go back to 900, this is still about a 20% improvement from 900 to 1.1 when normalized in this manner. We all know that per mass, in a sample limited case, you go to a smaller rotor. And if you can fill a 1.6 but not a 2.5, then you're generally going to want to stick with that smaller rotor. And again, as I noted earlier, at 750 megahertz, we can get the full benefit of a 3.2. At 900 megahertz, we can get the full benefit from a 2.5, but the 3.2 badly underperforms. And then at 1.1 gigahertz, a 1.6 millimeter is our best available at this time. Okay, so if you plot that now, according to the Holton-Richards equation, and plot here's n equals 24 points, which are all the rotor geometries from all the vendors, you get pretty good agreement. It's a power of 1.4, so it's not the 7/4 dependence, but it's certainly close and getting close to 3/2. If you excise the non-variant rotors, we just use variant 1.6 and 3.2 standard rotors, then you see a much better fit overall with those 17 data points, but again, about to the power 1.4. Okay, and that's a normalized signal noise, corrected for the noise figure of the spectrometer, and for the B1 efficiency. So that tells us that the trends can be reproduced as you go up in field, and the way you can improve its sensitivity is either by improving the efficiency, improving the noise figure, or obviously adding more sample. But if the probe dependent factors are the B1 efficiency as well as the homogeneity to contribute to the sample volume that's active, okay? So again, coming back to that example that I showed earlier, in a 4.5-hour experiment here, we see in a DAR mixing experiment, 750 megahertz, 12.5 kilohertz, we see the intra-residue correlations. Then you do a similar amount of time with 500 milliseconds mixing. And noting this is a fibril sample, so it's got line widths that are not quite as good as most microcrystals, although they're respectable. It's a sensitivity challenge. With the improved sensitivity, this is literally one of the before and after examples we have, because we then got all of these extra peaks corresponding to distances out to 8 to 10 angstroms in this synuclein structure, okay? And all those peaks that would otherwise be lost if you had a factor of 2 lower sensitivity are critical to that structure calculation, okay? So now I want to talk for the remaining time about proton detection, and in particular, how we can address cases where we don't have such narrow microcrystalline line widths, but we have real samples, fibrils, membrane proteins, large assemblies, RNAs, and other samples that have some significant T2 star contribution, some significant inhomogeneous broadening contribution. And so when we take samples of that sort and we put them into 1.6 millimeter rotors, we see, or smaller than 1.6 millimeter rotors, we see a significant reduction in sensitivity because we're not getting the full T2 benefit of spinning faster than 50 kilohertz, okay? So here's an example of an ideal case, which is GB1, using Rajat Garg's low power supercycle TPPM decoupling. If you back exchange to 25%, spin at 50 kilohertz, this is obviously in a 1.2 millimeter rotor, we can get line widths from 0.05 to 0.1 ppm, and that's GB1, but in fibrils and membrane proteins, we rarely see line widths quite that good, And so our calculation of signal noise needs to take that into account. And if we just go to a smaller rotor and spin faster, we don't see a significant benefit. Okay, so some of the challenges then of trying to develop sensitivity improvements in the probes is that when we take proton spectra, they're a convolution of the line shape effects and the probe. There's no good community standards for proton solid state NMR signal noise. And if you use a protein standard, you have to calibrate several factors. So just as I was saying earlier with NAV, if you have to calibrate a whole series of cross-polarization, decoupling, solvent suppression, and so on, the signal noise that you observe could very likely depend upon those parameters. If we use a neat solution NMR standard, those are far too high a signal noise and create a dynamic range problem. It also is not necessarily compatible with the types of experiments you want to be optimizing. So our proposed solution is a solid TMS analog, which has been used before for silicon NMR. And that is presented in a paper by Eric Hahn, also in JMR last year. And again, to briefly summarize, the purpose of TKS is we have this standard, which is like TMS times 4 with another silicon in the middle. And that is a solid form at room temperature. And you can pack in a rotor. And in fact, you can mix it with other samples, as I'll show momentarily. And you can measure that proton signal with high dynamic range. And you can also dilute that as needed into another solid, such as KBr. Okay, so what Eric did is he diluted the TKS 2.6 by weight into potassium bromide. And that now gives you a signal noise that's not in the tens or hundreds of thousands, but in the thousands, in a range that is compatible with the gain settings that you would use in a normal experiment. Okay, and so this can also be used to mix together multiple standards. So you have TKS with adamantane and N-acetylvaline. So we have our carbon sensitivity standard, as well as our proton sensitivity standard. We have our shimming and referencing standard, and KBr to check the magic angle. Now, when we're developing probes, we're often in a situation where we don't yet have the carbon and nitrogen channels built on the probe, and we want to test with the proton channel only. And so this is critical because we want to optimize that circuit for sensitivity. Okay, and so in this case, we want to use TKS directly to do the shimming and the magic angle adjustment and the sensitivity measurement. And so what you see here, as Eric showed, is that if you look at KBr, either the first or second order sidebands, and you go 1/1500th of a degree off the magic angle per step here, you get a decrease in the intensity of that sideband, as is well known as why this is an often used standard for setting the magic angle. With TKS, you can do a Hahn echo with approximately 8 milliseconds echo time, and you get a similar dynamic range. But also what you notice is the signal noise is much higher than in the case of the KBr. And in particular, if you don't have a carbon channel in your probe, the sensitivity benefit is infinite because you can't detect any potassium bromide. So we have this capability now to measure the magic angle with TKS, and then we can also do shimming, okay? And when we look at the line widths of TKS, although it's not as narrow as adamantane, it follows a very systematic behavior as a function of spinning rate. So if you plot the line width after shimming against the rotor period, and so this is spinning at 10, 12, 13, 16, and so on, up to about 33 kilohertz, and you plot those line widths and fit it to a line, what you see is the zero crossing, that is the line width in the infinite spinning speed limit, is about 6 hertz, okay? And then if you take that inhomogeneous line width from TKS, divide by 4 for 1.4 hertz, that's what you would expect the corresponding C13 line width to be. And in fact, that's what we see. So if we do that with the rotor with all 4 samples mixed together, we see a full width at half max in this example of 42 hertz at the 33 kilohertz spinning, and that corresponds to 1.16 hertz full width at half max for the adamantane. So that's about 7.7 parts per billion if you want to use that unit, and I think we do, because now our line widths are all typically in the single-digit part per billion range. The reason for that is because along with Phoenix NMR, and Yasmin and John have worked with Eric and others to develop magnetic susceptibility modeling for magic angle spinning modules. And briefly what they do is they take a model of the whole module, all the parts, the spinner, the rods, the nuts and washers, you name it, everything, and categorize the magnetic susceptibility, and then perform a 3-dimensional mesh model of the susceptibility. And what you see, for example, is a module that has 2 slits cut in it, gives a very distorted line shape. One with no slots works well, but of course, You can't practically use that because you can't get airflow in and out for VT, among other things. And so you have to have some holes. And if you do have holes, you want to symmetrically distribute them around the outside and do a calculation to ensure that that's symmetric. Then in addition, if you take a module that looked like this, you'd see large distortions due to extra pieces of plastic, say here and here. And so what they've done now is carved out the extra plastic according to a 3D model, and then they get a much better line width without any shimming, okay? And so the benefit of that, of course, is that you can shim faster and better. In a traditional design, you get about 4.3 hertz. This is in a 5 millimeter here. And now with the susceptibility optimized design, we're down to just over a hertz, which is about 20 parts per or 2 parts per billion. So then this also shows that you can get the majority of that benefit by using just a few shims, right? And so there may be circumstances in which it's beneficial for magic angle spinning probes to use a subset of the total shims, and that would make it easier to implement on magnet systems with narrow shims. I'll say just a couple more things. I think I have a few minutes left. About OPTO. This is an automation routine that allows us to do a much better job of reproducing data collection and optimization. That's published, so again, I won't go into detail. I'll skip over that in the interest of time. But Colin has a very nice paper in JAX, and we are distributing that software. It's a method for automated spectrometer parameter optimization. Can be used for any pulse sequence, reduces spectrometer operator time by a factor of 10, and that includes compared to how long it takes me to do the optimization myself. And it usually ends up with better signal noise. Okay. The final thing I'll point out is that we have a dual resonator design that we've developed with Phoenix NMR collaboratively. And so this is intended to improve the sensitivity for proton. A standard solenoid resonator would just have a solenoid inner coil. We have worked with John Stringer and Lauren Price and Colin Borsick in my lab to develop a dual coil resonator, which has the proton channel on an inner solenoid, has the X and Y channels on an outer saddle coil. We've tested this in NMRFAM and observed that at 600 megahertz, we get a 30% increase with a cross coil. And we also get a significant improvement in homogeneity, where the I450 over 90 is 80% as opposed to 69%. And that's at 600 megahertz. We then see an even bigger improvement when we look at protein samples or we go up in magnetic field. And so the reason you see a bigger improvement in protein samples is because both the proton resonator and the X and Y resonator have a substantially higher homogeneity than a standard design. And so what we see when we do that comparison using OPTO to reproduce things automatically, we get a sensitivity improvement of factor of 2 at 600 megahertz. And then if we go to 750, we get another factor of 56% improvement, matching the 7/4 expectation with magnetic field. So overall then at 750 with the cross coil compared to 600 with a standard coil, we're more than a factor of 2 better with the TKS standard and a factor of 3 with a protein such as GB1. And this also works quite well in doing 4D experiments. So here's a 4D experiment of GB1 collected in 22 hours with very high signal noise, where we're seeing distances out to at least 6 angstroms. And then that was reproduced also with synuclein. And so Colin has studied a synuclein fibril that's a new form, and is getting good 4D data at 750 megahertz in a matter of 24 to 48 hours, okay? And so that actually validates the distances relative to the cryo-EM structure of that form, and that sensitivity then generates a total of 2,076 long-range distance restraints, okay? I'll just show you, how much time do I have left? 2 minutes, maybe?
Yeah, it's fine.
Okay, so one more thing about 1.1 gigahertz, okay? So as you know, these high temperature superconducting magnets drift quite a bit. They settle down eventually, but still drift on the order of a half a ppm a day, and maybe down to a couple tenths of ppm per day. But especially when we were first installing this instrument, we noticed that this drift was not only strong, but also nonlinear. It had some bumps in it, okay? And so obviously you would say, well, let's incorporate a lock channel. Well, the lock channel is not available on the solids probes from Bruker, but we have incorporated these in collaboration with Peter Gorkoff and with John Stringer for the Black Fox and Phoenix probes. And if you measure, this is an example on our 900 system, with and without lock, you see a substantial improvement. And instead of 0.017 ppm field drift with sharp spikes, you get down to 0.001 ppm. the magnet at 1.1 the drift is larger, and the other challenge is that the sweet spot is smaller. Okay, so whereas at 900 and below, we typically have at least 60 millimeters of travel vertically. In this 1.1 gigahertz magnet, we only have about 35 millimeters of usable travel along the Z dimension. And so this shows relative to the top point, the highest you can get the probe, if you lower it down by 35 millimeters, you go from, you see a coil image here because the shims aren't on. We're just looking at the supercon shim effect. And we go down and we see below 35 millimeters, we no longer have a usable NMR signal. And so this becomes a problem a little bit with the black box design, which we use at 900, where the sample coil is here, the lock coil is here, and that delta is 32 millimeters. So even if we push this all the way up at the top, we have some difficulty getting a good line shape on the lock sample. Whereas if we redesign that, and with John, he designed a lock coil that now sits here, which is only 12 millimeters and slightly above the sample coil. So now we can put the sample coil in the sweet spot. The lock coil stays a little bit high. And so the best homogeneity is on the sample coil. We get that down with adamantane to 2.4 hertz. And then we can also lock with D2O in the lock coil. And the reason and then this is an expansion of the black box probe to show that geometry. But then we can run for several days to weeks and get homogeneity and stability within 1/10 of a part per million or better. This is an example of a 28 kilodalton microcrystalline protein, toho beta lactamase. Here's the comparison between 600 megahertz and 1.1 gigahertz. And then if you go to tryptophan synthase, which is 144 kilodaltons microcrystalline, it's a dimer of 72 kilodalton dimer. So it's effectively 72 kilodaltons or 655 residues. You can see the exceptional resolution in the carbon-carbon 2D. If you blow that up, you see the line widths are really sub 0.3 ppm, which is really the J coupling remaining. Okay, if you look at the NCO and NCA 2Ds, again, without homonuclear decoupling, you see splittings in the carbonyl region of the NCO. You also see broadening in the NCA. And so with Len Mueller, we worked on applying low bash decoupling in the direct dimension to eliminate those J couplings. And according to his paper from now more than 10 years ago, if you apply this windowed decoupling sequence, you can expect to remove the J coupling and reduce your line width by about 50 hertz for the carbonyl carbon. And that's in fact what we see if you look at the bash decoupled version on tryptophan synthase. And so then we get to the point where in that 2D spectrum, we can resolve close to 650 peaks, pretty much one per residue, although we haven't completed the assignments yet. This is to sort of gives an indication of the type of resolution that's available at 1.1 gigahertz if you have all these considerations taken into account, both the probe sensitivity, the homogeneity, the lock, and the overall system performance. Okay, so I'll stop there and thank you all for your attention, and I'd be happy to answer questions.
Thank you very much for the fantastic tutorial. So we learned a lot. Yeah, let's open the floor for questions. So I see we have questions here. Okay, so we have one from Julie. What would be your first recommendation for improvements to other labs with the standard probes?
Well, we have worked with both Black Fox and Phoenix, and depending on the type of probe you need for fluorine or proton or carbon or other nucleus detection, there are performance benefits from Black Fox for the carbon detection. The new design with Phoenix gives this factor of 2 for proton sensitivity. And then it would be a question of what rotor sizes you're interested in, what magnetic fields. But all of those offer, between 2 and 3-fold enhancement in sensitivity relative to some of the other commercially available probes.
Okay, cool. So I have a question, Axim. So when you started using the TKS standard for proton detection, did you try like real samples like fibrils after doing the standard? Did it make a big difference or no?
Absolutely. Well, yeah, I mean, it's better than adamantane for shimming because although there's an offset in the overall line width, as we showed, that is separable between the dipolar homogeneous contributions and the inhomogeneous contribution. So you can shim with TKS, get that to the best, converge to the best result, and it will match up perfectly with your adamantane line width, as we showed in terms of a ratio proton to carbon line width. That often also goes much faster because of the higher sensitivity for proton. And using the OPTO software, we can also shim directly on samples, and Colin showed that in his JAX paper. And so what we see is we shim with TKS or we shim with adamantane. That's necessary when you're first installing the probe. But then when you go to a real life sample, as you say, we can actually shim directly on the sample using the OPTO software along with the routines and the probes that we have. And then that reproduces to within the same resolution as it would for TKS and adamantane.
Okay, cool. So another question from Julie. Which factor was the most challenging to improve or change?
Yeah, so it's a contribution from several pieces, right? The efficiency of the probe, the biggest difference gained through both the black box design for carbon detection and from the new cross coil design for proton detection, is the overall efficiency of power transmission and reception to the coil. So when you have separate coils, and that's true also for the black box design, where the solenoid on the inner coil is optimized for carbon and the loop gap resonator for proton is outside. For the proton detection, we do it the opposite way, where we put the proton on the inside, the X and Y channel on the outside. And that in turn allows us to independently optimize the inner coil for the best possible efficiency. That can be up to a factor of 3 at ultra high field, right? We don't have a lot of data yet at 1.1 gigahertz on the cross coil, but we do have some early returns that indicate it's at least a factor of 2 better. And then you gain in addition in homogeneity. So not only do you get twice as much signal from the spins in the rotor that are within the active volume, but you also get additional sensitivity because you're capturing active volume in that rotor that you otherwise wouldn't, okay? So that's why when we do a protein experiment, we'll get even more benefit. And then the homogeneity overlap with the carbon channel and nitrogen channels is excellent. So, the short answer then is efficiency of the resonator, but also the homogeneity. And then there's factors, those are factors of 2 or 50%. And then the factors related to the noise figure can be on the order of 20 to 25%. And then there's other, those are the dominant 3 factors.
Okay, cool. So yeah, if you have questions, you can post them in the Q&A box. Okay, we have one. Oh, we have one comment. Brilliant. Okay.
Okay, thank you. In terms of availability of these probes, I'd also note that we're starting a company in Madison called Resonant, and we will be working with Black Fox and Phoenix to develop probes. And we hope also in the future to develop NMR consoles, although that's an early stage development. It's something that we hope to contribute, especially for solid state NMR, to the community.
Oh, that's cool. Okay, so we're gonna see if we have questions. We're gonna wait for maybe 2 minutes and for you to post questions. Yeah, we have one from Adrian. So for the additional preamp to reduce the noise figure, is this a fairly universal fix? For example, should everyone be going out to buy one for their system, or is it a targeted change?
Yeah, that's a good question. It really depends upon the noise figure measurement that you make at the preamplifier. And so I wouldn't just say throw in a preamp without doing some diagnostics first, but you can measure the noise figure with a calibrated noise source at the preamplifier output. And if that noise figure differs from the noise figure of the spectrometer as a whole, then you would benefit from an insertion of an additional preamplifier. And so you can measure the noise figure with the spectrometer, measure it separately just with the preamplifier. If that difference is more than 1 dB, then you can certainly benefit by incorporating additional preamp. The other thing you could do if you don't have noise figure measurement equipment in your lab is you could procure one of these preamps from ARR, Advanced Receiver Research. They're about $150 for the non-magnetic preamps. You cable them according to how we described it in the SI over JMR paper and just test with NAV to see if your signal noise improves. And I would encourage you also, when you do that, to measure as a function of gain, because very often the receiver on the spectrometer where the gain stages are included is the noisiest part of the spectrometer receiver chain. So you want to make sure that your signal is far above the noise floor as it comes into the receiver for digitization, and that can be tested by simply inserting that preamp.
Mm-hmm.
Johan has a question, does the dual coil work with CP? The answer is yes, it does, and we showed CP spectra there for GB1 and synuclein. We use lower power conditions, to be fair, because the X and Y channels with a larger volume saddle coil don't achieve quite the same pulse widths as you would with a standard solenoid. And so the trade-off is that we're getting approximately factor 2 better proton performance. You might give up a little bit of that in cross-polarization performance by using lower power conditions. And to give you some real numbers, like the carbon pulse width on the 1.6 would be about 5 microseconds rather than 3 or 2. The nitrogen pulse width would be about 10. And we think we can shorten those a little bit in the next iteration of the design. But as it is, you can use low power CP conditions, or you can use inept transfers, which actually in many cases are superior. And the inept transfers work equally well regardless of the amplitude of those fields, okay? So question about TKS for checking magic angle and shimming at slower magic angle spinning rates, 15 to 20 kilohertz and 3.2 millimeter rotors, for example. The answer is yes, you could do that. The line width will be approximately 100 hertz at 15 kilohertz spinning because you have a larger dipolar contribution. But because you have a very high signal noise ratio, even a difference between 100 and 105 hertz is very straightforward to detect, in particular if you use OPTO automation. And so we'd be happy to help set you up with OPTO automation. And then you can shim with TKS at any spinning rate desired. And it doesn't matter to the algorithm because it's getting very high signal noise measurements. For the magic angle, the issue is you want to pick an echo time that's approximately 2 to 3 times the T2. So you're using that signal noise to amplify the effect of magic angle misset by going out to 2 to 3 times the T2 at the particular spinning rate you're at. If you're spinning at 25 kilohertz, that would be about 8 milliseconds. At 15 kilohertz, it's going to be about 5 milliseconds or 4 milliseconds. So your echo time might be around 8 to 10, okay? Heal and recovery system question. Yeah, so I think in the interest of time, I won't go into the whole details, but I would encourage you to follow up with our NMRFAM staff members, Paulo Falco Cobra and Alex Patterson, and you can find them on the NMRFAM website. We've configured here a system that allows us to recover approximately 100 liters of boil off when we fill high field magnets. If you have a high field magnet, that's sort of the threshold you need to achieve to capture all the helium. A lower field magnet, you wouldn't need such large bags. But it depends, the scaling of the investment depends on how many magnets you have and what the largest fill volume is.
One more, I think.
Is there any more questions?
Yeah, we have from Asif.
Okay.
Yeah, so he say, I'm interested in heteronuclear decoupling. Does proton decoupling become challenging at higher magnetic field due to the higher CSA?
In fact, I think it's not much more challenging, either for proton decoupling with X observe or X decoupling with proton observe. In both cases, as you're spinning a bit faster and going up to such high magnetic field, the spin system is much more dynamically inhomogeneous. So pulse sequences with supercycles tend to work better at high magnetic field. And that in part, Asif, is probably because it's compensating for CSA cross terms with a dipolar coupling, right? So that's the Matthias Ernst study from many years ago where he showed this proton CSA relative to the dipolar coupling H to N. And supercycle TPPM therefore works really well. Waltz decoupling, a reviewer pointed out to us, also works quite well. And there's, I think, future opportunities to combine those two strategies and maybe even make it better. And then at high power, similar strategies work really well. So for example, Spinal 64, we find works really best among all the standard sequences. And we have some supercycle TPPM variants that maybe will be better than Spinal but we don't yet have that reproduced sufficiently well. So hopefully we'll have an update on that soon.